three-dimensional isotropic harmonic oscillator. An isotropic harmonic oscillator has the potential energy function U of x, y, and z is 1/2 k prime parentheses x squared plus y squared plus z squared. Isotropic means that the force constant k prime is the same in all three coordinate directions. Part A, show that for this potential, a solution to the time-independent three-dimensional Schrödinger equation is given by psi equals psi sub nx of x, psi sub ny of y, and psi sub nz of z. In this expression, psi sub nx of x is a solution to the one-dimensional harmonic oscillator Schrödinger equation with energy E sub nx equals nx plus 1/2 parentheses h bar omega. The functions psi and y of y and psi and z of z are analogous one-dimensional wave functions for oscillations in the y and z directions. Find the energy associated with this wave function psi. Okay, so we're going to write down the one-dimensional harmonic oscillator Schrödinger equation on the x-axis, y-axis, and z-axis. So we can start with the x-axis minus h bar squared divided by 2m, second derivative of the one-dimensional wave function psi sub nx of x dx squared plus 1 over 2 k prime, the potential term, x squared applied to the wave function psi sub nx of x is equal to energy sub nx psi sub nx of x. That's the one-dimensional harmonic oscillator Schrödinger equation written for the x-axis. Now for the y-axis oscillations, I have an analogous equation minus h bar squared over 2m. This time I'm taking the second derivative of psi sub ny of y with respect to y plus the potential energy term 1 over 2 k prime y squared psi sub ny of y is equal to energy sub ny psi sub ny of y. And finally, I can write it for the z-axis minus h bar squared over 2m, second derivative d squared psi sub nz of z dz squared plus the potential energy term 1 over 2 k prime z squared psi sub nz of z is equal to E sub nz psi sub nz of z. So we have all of these one-dimensional harmonic oscillator Schrödinger equations. Now what I'm going to do is I'm going to multiply the first equation with psi sub ny of y and psi sub nz of z. The second equation by psi sub nx of x and psi sub nz of z, and the third equation by psi sub nx of x and psi sub ny of y. And then add these up. So if I add these up after multiplying with these terms, I'm going to get a long equation. So here it is. Minus h bar squared over 2m. Then I have psi sub ny of y, psi sub nz of z multiplied by second derivative d square psi sub nx of x dx squared, the first term. Then I will have psi sub nx of x, psi sub nz of z, second derivative d squared psi ny of y dy squared, and then the third term psi sub nx of x, psi sub ny of y, the second derivative d square psi sub nz of z dz square, and then I'm going to add to it the potential energy term. So I will have, let's do it in the second line here, plus 1 over 2 k prime x square plus y square plus z square psi sub nx of x, psi sub ny of y, psi sub nz of z. This is equal to e sub nx plus e sub ny plus e sub nz multiplied with psi sub nx of x, psi sub ny of y, and psi sub nz of z. Okay, so let me double check what I did here. When I multiply it with these terms, you can see that they all have the same factor here, psi sub nx of x, psi sub ny of y, psi sub nz of z, x, y, z, x, y, z. So they add up. So that gives me this term. And for the potential energy terms, likewise, I have the same terms here multiplied by 1/2 k prime. Then I have x squared plus y squared plus z squared. So that gives me this term. And for these terms, I have the first one, for example, ny and nz multiplied by second derivative with respect to x, etc. So this is what I have. Now I note that if I have this wave function as a function of x, y, and z, if I take a partial derivative, second derivative with respect to x, that means I'm going to leave the y dependence and z dependence alone. So I'm going to have psi sub ny of y and psi sub nz of z alone, and I'm taking the second derivative with respect to x of the psi sub nx of x. So this is true if I have the wave function that can be written as a product of psi sub nx of x, psi sub ny of y, and psi sub nz of z. And the same thing is true for the partial derivative with respect to y and partial derivative with respect to z. So what I observe here, the first term here, for example, is actually the partial derivative with respect to x. So with that, I can write the Schrödinger equation as minus h bar squared over 2m. Now the first term there becomes the partial derivative with respect to x, del square, del x squared. The second term becomes partial derivative with respect to y, so it's del square, del y square. And the third term becomes partial derivative with respect to z, second derivative, del z square, applied to the wave function psi sub n of, as a function of x, y, and z. Then I have the potential energy term 1 over 2 k prime x squared plus y squared plus z squared multiplied by my three-dimensional wave function psi n of x, y, and z, and this must be equal to the sum of the energies E sub nx plus E sub ny plus E sub nz multiplied by the wave function multiplied by psi sub n of x, y, and z. So that's the form of the Schrödinger equation I recognize here. And with that, the energy of this oscillator can be written as E sub n is equal to E sub nx plus E sub ny plus E sub nz. All right, so we were supposed to find the energy associated with this wave function, and provided that we have a wave function of this form, we have shown that this is a solution of this potential if this wave function can be written as a product of its x, y, and z dependencies like this, and basically we can form the three-dimensional harmonic oscillator Schrödinger equation in this form by assuming solutions of this form. Now, in part B, from your results in part A, what are the ground level and first excited level energies of the three-dimensional isotropic oscillator? Now, since we have the following energy levels for the one-dimensional harmonic oscillator, E sub nx is equal to n sub x plus 1 over 2 h bar omega. N sub x is an integer, remember. And we have for the y-axis, E sub ny is equal to quantum number n sub y plus 1 over 2 h bar omega. And likewise for the oscillations on the z-axis, E sub nz is equal to n sub z plus 1 over 2 h bar omega. So we have all of these energy terms. Now we have discovered in part A that the total energy of the three-dimensional isotropic oscillator is the sum of these three energies, n sub x plus n sub y plus n sub z plus 3 over 2 h bar omega. So that's how I calculate the energies for the three-dimensional isotropic harmonic oscillator. And that gives me for the ground state energy E, smallest possible values of the quantum numbers are 0, is 3 over 2 h bar omega. And for the first excited state, we can have one of them being 1, E100 or E010 or E001 is equal to, if one of these is 1, the others are 0, you will have 5 over 2 h bar omega for the first excited state energy. All right, and let's move on to part C. Show that there is only one state, one set of quantum numbers for the ground level, but 3 states for the first excited level. Actually, I've already done that, but let's redo it here. Ground level corresponds to this energy E sub 0 is equal to 3 over 2 h bar omega. And the combination of quantum numbers that give me this result are nx is equal to 0, and y is equal to 0, and Z is equal to 0, which is describing only one state. On the other hand, for the first excited state, so the first excited level, we have the corresponding energy E1 equals 5 over 2 h bar omega. Now, which combinations of the quantum numbers give me that? N sub x is equal to 1, n sub y is equal to 0, n sub z is equal to 0 is one possibility, n sub x is equal to 0, n sub y is equal to 1, n sub z is equal to 0 is another possibility, n sub x is equal to 0, n sub y is equal to 0, n sub z is equal to 1 is another possibility. So these just give me 3 states. So there are 3 combinations. So as suggested by part C, we have only one state, one set of quantum numbers that correspond to the ground state energy, but 3 distinct set of quantum numbers corresponding to the first excited level that is described here. Okay, so in this problem we have talked about the three-dimensional isotropic harmonic oscillator where the force constant is the same in all 3 coordinate directions. And by assuming solutions of the form which are products of x dependency, y dependency, and z dependency, we have shown that the energy of the three-dimensional isotropic oscillator, harmonic oscillator, can be written as the sum of the energies of the corresponding one-dimensional harmonic oscillators on x, y, and z axis, by noting that we can multiply these 3 different Schrödinger equations with these factors and add them up, and we realize that the partial derivatives are hidden in this equation, and therefore this has the form of the Schrödinger equation for the three-dimensional harmonic oscillator with the total energy E sub nx plus E sub ny plus E sub nz. These integers n sub x, n sub y, n sub z have the smallest possible value 0, corresponding to ground state energy, total energy 3 over 2 h bar omega, and the next highest, the next level will have one of them equal to 1, the others equal to 0, corresponding to energy 5 over 2 h bar omega, which corresponds to these 3 combinations, so 3 states, but for the ground level we only have one set of quantum numbers that gives us this ground state energy.